So today we're going to talk a little bit about probability concepts and rules. A probability is a numerical value that measures the likelihood that an event occurs. And a probability value ranges between 0 and 1. When the probability is 0, it is impossible. It means you have an impossible event that can never occur. Meanwhile, a 1 reflects a definite event that will always occur. An experiment is a process leading to one of several possible outcomes, and the outcome may not be known with certainty before the experiment begins. And for one example that we can consider is changing a branding strategy. We may have some ideas about what we want to do to change our branding strategy, but we may have to rely on sort of some empirical information and develop some probabilities to decide what is and is not worth the risk, or what share of customers we will like or dislike the product. So the sample space of an experiment is denoted with this italicized capital S, and what it is that it contains all of the possible outcomes of an experiment. So there are a few different examples that are probably very salient to you, like letter grades in a course. In this class, all of the possible outcomes for your grades are A, B, C, D, and F. But hopefully most of you will be in A and B territory. At the end of the spring 2020 semester, the sample space was, if you so chose, fail, pass, and high pass. So those are our sample space. Those are all of the possible outcomes from a given scenario. Meanwhile, an event is any subset of outcomes of the experiment. And sometimes it may only include a single outcome, but there are scenarios where they may contain several outcomes. For example, if we consider what a passing grade is, A, B, C, and D, those are events. We don't include F because we're only interested in what events would yield a pass. So a little bit more on events. We have exhaustive events and all possible outcomes of an experiment belonging to the events, and they include all of the outcomes in the sample space. So these are exhaustive, and exhaustive means it includes everything in great detail. Meanwhile, mutually exclusive events share no common outcomes. The occurrence of one event precludes the occurrence of the others. So when you think about your final class grade, you cannot simultaneously have an A and a C. Your grade, your final course grade, is mutually exclusive. If you have one, you don't have any of the others. However, grades of A and B are not exhaustive events because they don't include all of the feasible grades in the sample space. But the events themselves, as I said, these are mutually exclusive. Pass and fail, on the other hand, are exhaustive, and they are also mutually exclusive. You cannot simultaneously pass and fail an entire course. Although, I don't know, sometimes it feels that way. So we can define events based on one or more outcomes of an experiment, or combine events to form new events. A really easy way, in my opinion, to visualize a lot of probability things is using Venn diagrams, where in this scenario we have a Venn diagram. The sample space is our big yellow rectangle, and the two tan, brownish, beigeish circles represents events A and B. The union of two events is denoted by A, the union symbol, and B, and it considers all of the outcomes in A or B or in that overlapping section. A similar concept is the intersection of two events, which is denoted by A, the intersection symbol, and the letter B. And these are, we can consider all of the outcomes in A and B, but the intersection is the portion of the Venn diagram that is included in both A and B that overlap. Then we may have the complement of an event. So A is our event, and it's denoted by this red circle with an A in it. The complement of event A is all of the rest of the space in the sample space that is not held within A. Again, using Venn diagrams like this can be very helpful, especially if you're more of a visual learner or probability just isn't super intuitive to you. I encourage drawing lots of pictures when you try to solve probability problems. I know it is something that worked out really well for me. And I like to pass on good advice when I can. So there are some defining probabilities, or defining properties of probability. And the probability of an event A, is a value between 0 and 1. And I have that illustrated mathematically. The sum of the probabilities of any list of mutually exclusive and exhaustive events equals 1. If you sum up all of your probabilities and you come to find a value greater than 1, go back and check your work, talk to your classmates, reach out to me, because it means we have some troubleshooting to do. There are also 3 general types of probabilities. We have subjective, which are calculated by drawing on personal and subjective judgment. Empirical, which are calculated as a relative frequency of occurrence. And classical, which is based on logical analysis. So we have some specific rules that support our relationships in probability. The first one we're going to talk about here is the complement rule, and that is the probability of the complement of an event is equal to 1 minus the probability of the event. So if we wanted to calculate the complement of A, we would subtract that red circle, that space that is associated with A, from 1. Would also mean that if you added the probability of A occurring and the probability of the complement of A occurring, it would equal 1, which is one of those fundamental properties of probability. So let's consider an example. 37% of female open house attendees will purchase a membership. So what is the probability that a randomly selected female will not purchase a membership? So we define A as the event that a randomly selected female will purchase a membership. And we can illustrate that as the probability of A is 37% or 0.37. And then we want to go ahead and calculate the complement to A. And we do that with this equation where we have the probability of the complement of A. We subtract the probability of A from 1. 1 minus 0.37 gives us 0.63 or 63%. So there's about a 63% chance that randomly selected female will not purchase a membership for the club. Another rule that is very common in probability is the addition rule, and this is used to find the probability of the union of two events. The probability that A or B occurs, or that at least one of these events occurs. And we have this rule because we don't want to double count anything. So the addition rule says that we'll add together the probabilities of event A and event B, but from those we need to subtract the intersection of A and B, because if we don't, we're double counting the probability of things that happen in that overlapping area. So we have to do a little subtraction even though it's the addition rule. So let's consider another example. Anthony believes he has a 75% chance of getting an A in statistics, and I hope most of you are feeling even better than that, and a 55% chance of getting an A in managerial economics. He also believes he has a 40% chance of getting an A in both classes. So what's the probability that he gets an A in at least one of these courses, and what's the probability that he does not get an A in either of these courses? The probability that he does not earn an A in either course is the complement of the union, and that is illustrated with the funky probability equation on the slide. So we can use the complement rule to address this problem. So we can let the probability of A sub s correspond to the probability of getting an A in statistics. So A sub s, S is for statistics. That's 0.75. And then the probability of getting an A in managerial economics, A sub m, M for managerial economics, is 55. And we know that the intersection, the probability of getting A's in both, is 0.40. So we can add all these things together and we find a value that is much larger than 1. So we know we can't just add this stuff together. We've already gone that far. We know that much. So now we want to use the addition rule to get to the bottom of this problem. So here, to find the union of getting an A in statistics and an A in managerial economics, we add together the probability of getting the A in statistics and the A in managerial economics, and we subtract from that the intersection between the A in statistics and the A in managerial economics. And there is a mistake in this formula between the probability of A sub s and the probability of A sub m. That should be a plus sign and not a negative sign. But we find that if we add 0.75 and 0.55 and then subtract 0.4, we find there's a 90% chance. So what we find is that the probability that he does not earn an A in either course is the complement of the union. So we can use this complement rule after we use our addition rule to subtract from 1 the possibility of him getting an A in at least one class, and we find that 1 minus 0.9 is equal to 0.1, or there's a 10% chance that he is not going to get an A in anything. But I'm confident that's not going to be a problem for almost all of you in this class. So another interesting relationship we have in probability is mutually exclusive events. So again, we'll use the example of events A and B, and the probability of their intersection is 0. So we don't need to worry about double counting because there is absolutely no overlap between events A and B. So if we're trying to figure out the union of the events, we can just simply add them together, and that's mutually exclusive events. It's one event cannot occur if the other has. So for example, I had to go to Cleveland, Ohio over the weekend, and I was not simultaneously visiting Pittsburgh. I could be in Cleveland or Pittsburgh, but I could not be in both at the exact same time. That's an example of mutually exclusive events. So let's consider another practical application of probability. So suppose the probability that a recent business school graduate finds a job is 80%. So event A is going to be finding a job, and it's 80% or 0.8. This is not conditional on another event, so it is an unconditional probability. However, the probability of finding a suitable job is 90% or 0.9 if the recent graduate has prior work experience. So now we can let B represent prior work experience, and we find that the probability of finding that suitable job is 0.9 or 90%. The probability that event is conditional on the occurrence of another event is called a conditional probability. So the probability of finding a suitable job increases from 80% to 90% when conditioned on prior work experience. So if you haven't thought about it yet, you might want to stroll on down virtually to the CCD and see about getting yourself hooked up with a sweet internship for the summer. So given two events, A and B are old friends, each with a positive probability of occurring, the probability that A occurs given that B has occurred is derived using this formula where we have the probability of the intersection of A and B divided by the probability of event B. Because the probability of A given B is conditional on B, that B has occurred, the sample space reduces to B. The probability of A given B is the intersection portion in the Venn diagram that is included in B, and the opposite is also true. The conditional probability of A given B is greater than the unconditional probability of A when B exerts a positive influence on A. And the conditional probability of A given B is less than the unconditional probability of A when B exerts a negative influence on A. So this is just a bit of a heads up to pay attention to the numbers that you're using to plug into your problems to figure out how to best interpret your findings. So let's consider yet another problem. An economist predicts a 60% chance that country A will perform poorly and a 25% chance that country B will perform poorly. There is also a 16% chance that both countries will perform poorly. So what is the probability that country A performs poorly given that country B performs poorly? And think about it for a moment before moving on with the lecture. So we're going to let event A represent the event that country A performs poorly, and that's 60%. And we can let B represent the event that country B performs poorly. That's 25%. The probability that country A performs poorly and country B performs poorly is the intersection of A and B, which is 16%. The probability that country A performs poorly given country B performs poorly is illustrated by dividing the intersection of the events A and B divided by B. And then that numerically becomes 16% divided by 25%. There is an extra 0 and decimal point on this slide. My bad. But we find that the probability that country A performs poorly given country B performs poorly is 64%. And the conditional probability is greater than the unconditional probability. So country B performing poorly exerts a positive influence on country A performing poorly as well. With the increases in globalization, countries are rely more and more on each other than ever before. And in fact, it's often joked that when America catches a cold, Canada gets the flu, because the economies of the two countries are so tightly linked. They support each other very, very strongly, and when one struggles, there's a high probability that the other one will as well. And we would also find the same thing between the United States and China, or the member states of the European Union. So we can find the joint probability as the product of the probabilities using the conditional probability formula. And we call this the multiplication rule. So the joint probability of events A and B are calculated by multiplying the probability of A given B times the probability of B. So considering an example, a manager believes that 14% of customers will respond positively to the firm's social media, and 24% of those responding positively will become loyal customers. So what's the probability the next recipient of their social media campaign will react positively and then become a loyal customer? Let's take a look. So we're going to let R represent the event that a consumer responds positively to a social media campaign. Note that so far we've generally used A and B to denote events, but you can use whatever letter you like. You can even use full words. Again, do what helps you the most. So the event that a customer or a consumer responds positively to a social media campaign is 14% or 0.14. L represents the event that a consumer is loyal. So the probability of L given R is 24%. So the probability that a consumer responds positively to a social media campaign and is loyal is calculated by multiplying the probability of L given R multiplied by the probability of R. So what we get here is 0.24 times 0.14 for a probability of 0.0336, so 3.36%. It's not quite as exciting as I would have hoped it would be, but we do these exercises so we understand business phenomena better. Another important concept is independence. If the occurrence of one event does not affect the probability of the occurrence of the other event. Events are considered dependent if the occurrence of one is related to the probability of the occurrence of the other event. So two events, A and B, are independent if the probability of A given B is equal to the probability of A, or the intersection of A and B is equal to the probability of A multiplied by the probability of B. I like the sports analogy for considering independent events. So, I am a big Penn State fan, and growing up in the Pacific Northwest, I really like the Seahawks. And during a given week, I might follow both of their games, assuming things are normal and everybody's playing and the stands are full and we've got a lot of good energy. Some weeks neither team wins, and other weeks both teams win. But there is absolutely no relationship where one win influences the other win. It's just a good football weekend when your favorite NFL and your favorite college football team win a game. So those are totally independent events. We just get really excited when we can chalk up 2 wins in 1 week. So another concept to think about, another example, is that suppose for a given year there's a 2% chance that your desktop computer will crash. Probably more now, given that there are fewer and fewer desktop computers being sold, and a lot of us are turning to desktops that can plug into really sweet desk setups with multiple monitors. And a 6% chance that the laptop will crash. Moreover, there is a 12% chance that both computers will crash. Is the reliability of the 2 computers independent of each other? Well, let's take a look. So D is going to represent the outcome that your desktop crashes, and that's 2%. And then L is going to represent the outcome that your laptop crashes, and that is 6%. So the joint probability of both of these things happening is less than 1%. And we can calculate the failure of the desktop given the laptop's failure as being 0.0012 divided by the probability the laptop crashes, and we find that gives us a result of 2%. So if your laptop crashes, it does not alter the probability that your desktop also crashes. So the probability of our desktop crashing in the very second line of the slide is 2%. But then when we calculate the probability of the desktop crashing given the laptop crashing, we find we still end up with 0.2. So the reliability of the 2 computers is entirely independent. That's all I have this time. Keep up the great work. I hope you enjoyed this whirlwind tour of probability, and I'll catch you next time.